One simple problem. So
Going live. Here we go. So let's start. So, this whole unit here, guys, is about basically extending the ideas of the derivative. That's why they call it differentiation. So it's extending the idea of the derivative onto curves and relationships that aren't necessarily functions. Like this first one we're going to look at is not a function. Real quick, let me just show you this. I've shown you this kind of stuff before, I think, in pre-calc, but just to give you a little primer here. Yeah, you're right. It is. So let's tilt this real quick. So if you ever, gone into Desmos and just kind of messed around and, you go like, oh, y cubed plus x equals y or something. There's a curve that, is that a function? No, but logically, there's nothing stopping us from talking about, like, say, is everything okay back there? Okay. There's logically nothing stopping us from talking about, like, say, oh, this could be draw a tangent line right there and then talk about its slope, right? So all this is, so don't let it scare you. It's just talking about how do derivatives factor into a weird curve like this. Or like, we probably make it look weirder. Like you can get all sorts of wacky. That's the
coolest thing I've ever seen.
Makes me nervous.
So there's a whole family of these things. You can go on. They're called elliptic curves. Are very fascinating. There's a whole family of these weird curves you can draw. This is a very limited family, but they get used in cryptography. Like encoding information, so malicious people can't like crack your code. Anyway, here's some general form, but anyway, so I just want to give you a quick little lead in there. So if you can write pretty much any equation you want. Oh, I guess last one. Has anyone ever just typed in a bunch of random stuff in here, like sine of x plus y squared equals 3x plus y minus the tangent of x? You can just. I've seen some of you guys. I think.
Wait, can you scroll down a little bit?
Yeah.
Whoa, that's lit.
What if it's plus tangent? Okay. All I'm saying is you can type in pretty much anything you want into there.
I've tested those.
And then you could then go, well, is it possible in theory to talk about derivatives of this of this curve? Okay, so sometimes you can watch this. This would be really good. X squared plus y squared equals -2. Oh, get it? Because there are no xy pairs that satisfy. No real xy pairs that satisfy.
Yeah.
Okay, so that was just a good little amount for you.
Oh, wow.
That
really got me.
Yeah, you got pranked. All right, so I think that was Winslow said identify this first curve. That is a circle. Yeah, so quick little review here. Why is that a circle? I know I've mentioned this before. Let's say it one more time. Because if you describe the set of all points, xy points, and then you draw this little right triangle, it's your good old buddy, the Pythagorean theorem, because this leg is x, this leg is y, this is the radius. So it would be true for any point on this set of points that x squared plus y squared equals r squared. So anytime you see an equation of that form, you want to think, oh, that's describing a circle. So like Trey said, this r here, in this case, it's the 16, is 4. So this curve is describing this circle. Okay, so x squared plus y squared equals 16. Okay, Now, this says, write an equation for the derivative, dy over dx. So how do you do that? You take the derivative with respect to x. So there's only one little trick here. It's actually a very easy trick. I think you guys will find this not too daunting. What's the derivative of x squared? 2x. Very good. What's the derivative of y squared? 2y times y prime. Because that's called the chain rule. Remember the chain rule? We a lot of times were using u's before, right? We'd say something like, oh, what's the derivative of u to the 4th power? You'd be like, oh, it's just 4u cubed, but you got to tack on that u prime. Does that ring a bell for everyone? Question?
Why didn't you do that for the x?
Very good question. So we're taking the derivative with respect to x. So that means, like when you write, this notation says, we're treating x like our variable, and anything that's not x, you would assume is some function that depends on x, unless otherwise stated. If you guys go on to like what they call like multivariate calculus, like a higher level of calculus, you get into these more nuanced distinctions of like, oh, is that thing a function of x or is it a function of something else? But for our purposes, you can pretty much 99.9% of the time, we're talking about either taking the derivative with respect to x or with sometimes t. You know, we did all those problems involving time.
Is there a special way to denote that if you're taking the derivative?
Yeah, so this, when you write this d over dx, this basically is notation for take the derivative of this thing with respect to this variable. So just a quick example, like you can go, what's d over d, the symbol could be like a little heart or something. Like that could be your variable, any symbol you want. So d over d heart of heart cubed would be 3 heart squared. But d over d smiley face, that's a different symbol of heart cubed. Well, now you'd have to go, oh, I think heart must be some function of smiley. So it would be 3 heart squared times heart prime, where heart prime represents the derivative of heart with respect to the smiley face. Cool beans?
Heart cubed must be a
Yes.
function of smiley.
Taking the sort of, if you go
Taylor.
the opposite way, would it be 2x times x prime, then it's 2y plus 2y, correct?
Yeah, so if you wanted to take the derivative with respect to y, it would effectively flip everything over. And then you'd be talking about dx over dy, which would be the reciprocal of your slope. Let's just rewind here. I think I don't want to get too much into this here. This is important stuff to think about. I
Yes.
mean, because there's nothing special about this symbol here. It's just 2 little lines that do this. It could be anything, right?
You could say that about most things.
They're just symbols.
Y prime or something? I don't remember.
So when you think, okay, so let's come back down to what are we talking about? Ultimately, we're trying to derive a formula, right? The formula is going to tell us about stuff like this. What's the slope of this? It's rise over run, right? A change in y over change in x. So for the last 5-6 years of your education, there's been this concept called slope, right? And this ties into that. Now, if we lived in a different culture that for some reason wanted to talk about run over rise, then this would all be upside down. We'd be talking about dx over dy. Does that make sense?
Yes.
But we, just whatever reason, I mean, the reason I think is because the bigger the slope, the steeper it is, right? A slope of 6 is steeper than a slope of 1/2, right? So
Nice.
okay, anyway, so think of this. So if you want the change in y over the change in x, that means you're taking the derivative with respect to x. So anyway, so x's are, now this might really throw you off. Pretty soon we're going to say, well, what if I want the derivative of this curve with respect to time? So what if I want like this, what if I want to say a particle is traveling along this curve? I want to describe its velocity or something. That's going to be a different question. But
I want you to take the derivative.
yeah, it would be with respect to time. It would be d over dt, and you'd have 2xx prime plus 2yy prime. and those primes would be with respect to t.
Wow.
That's okay. Rewinding. We just want to know what the slope is. So taking the derivative with respect to x. So x is just a variable. Derivative of x squared is 2x. Derivative of y squared, you say, oh, y is kind of like a function of x here, so 2y prime. And then what's the derivative of 16? 0. Okay, now this is the thing we really care about right there. That is dy over dx. That's a big important thing. Y prime is just a different way of writing the slope. So if I solve this, you get this, which is going to have, it's a lot more nice and like satisfying than it might look at first, because it makes perfect sense now that we have that formula. What do I mean? Where on the circle is the slope 0?
At the tippy top
The tippy top
and the body.
and the bottom. Would you agree that, do you see how that agrees with this formula?
Yeah.
Because basically what that says is when x is 0, the slope is 0. Right?
Yeah.
You all right over there?
No cracking up over her.
Okay. How about this? Where does this thing have a vertical tangent line? Where's the slope undefined?
-4.
Well, don't think of the x value, think of the y value. What happens?
Oh, 0.
When the y value is 0, right?
Oh.
So when the y value is 0, you have a infinite slope, right? You're kind of like dividing by 0. Does that make sense?
Yes.
A rise over no run. And then you can even look at stuff like, let's say your x and the y value were the same size. Say x and y were the same number.
Whoa.
You'd have a slope of -1, right?
Mm-hmm.
And then likewise, if x and y were opposite numbers, you'd have a +1 slope.
That shape on that.
So
thing
hopefully
looked up
that
makes
all
sense
like,
now.
now that was kind of a quick explanation, but the key here, the goal is to understand how this final formula connects back to geometrically what's happening in the curve. So now sometimes it's going to be too complicated. Like on number 2,
Answer the
by the way, I mean, I kind of covered all the points here. So it says, at what points is the derivative 0? Well, at 0, 4, and 0, -4. At what points is the derivative undefined? Undefined derivative in this case would have to be a vertical tangent line. So 4, 0, and -4, 0. And then, of course, the curve with the tangent lines. I drew some extra ones in there. But do we feel semi okay about that? Feel, yes, Aiden.
So really, when you're taking the derivative of this, it's whatever, if you're taking the derivative in terms of x there, like the second equation, you would take it and it would be the 3x to the second power plus 2y times, and you just add a y prime. Just literally take that as y and then just add a y prime. Whatever the derivative of that.
I know you mean multiply, but yes, you are putting a little y prime multiplied on to that term, yeah.
Okay.
And then like on 3, what we're going to find is we got to use the product rule with the chain rule. We're going to go over a bunch of examples. We're not going to stop there. But yes, you're totally right. So if you're being asked to find this quantity, just remember there's maybe 2 or 3 things to remember. If you're being asked to find this, you are being asked to find a slope. Know that. So that's talking about a slope. Also know that this can be written shorthand as y prime. That's another big thing to know. And then the last thing is to understand that this symbol here, which is usually an x, that's going to be your variable. So any other symbol you encounter, you can assume, so you encounter a y in your formula, assume that y is a function of x. Or if you see a u in your formula, assume that u is a function of x. Okay. And by function of x, I mean it's some quantity that depends on the value of x. Okay, so like I shouldn't say function, really, it's not really a function. Okay, let's look at 2. So Aiden, you already pretty much told us the derivative, that's good, so, if you heard what he said, this one we should also graph this in the computer to see if the computer, if the geometry agrees with the image that we come up with, so. Derivative would be
Yeah, forgot the Y.
now if you solve that, now we're in calculus, so I don't think you need to show every little algebra step. If you can go straight from this to this, I'd say that's totally fine. Make sense?
Yep.
So, what that means, that's all the question is asking us to do, is what's the equation for, well, there you go.
So that's space for that.
So if I graph this curve on a computer, was it x, was x? You can see, do you see how that my formula over there tells us that anytime y is 0 on this curve, we're going to have a vertical tangent line? You can draw the tangent lines if you want. Sure, it wasn't that hard to visualize them, but there you go. There's your vertical tangent lines. And then maybe more interestingly, what's the condition for us to have a horizontal tangent line?
X has to be,
Something about x, yep.
X has to be, the square root of 1.
The square root of 1/3. So does that make sense?
Yeah.
So if I ask the question, where does this thing have a horizontal tangent line? I would set this equal to 0 and solve, and you'd get, if you set that equal to 0, you'd get plus or minus square root of 1/3. And that would be the condition. So what you'd say is, if there are any points on this curve that have these x values, they would have to have horizontal tangent lines there. And you can see right here, let's just confirm. Oh, great machine, what is the square root of 1/3? It's about 0.577, which you can see is the x value of the curve where it's hitting that horizontal tangent line.
Great machine.
Oh, great machine. So, anyway, I guess my point is that this formula tells you a lot of information about the curve itself. It tells you about where does this thing have, and that's an elliptic curve, by the way.
The elliptic curve. I think they're so hilarious. I might be the only one who thinks that.
What?
It's maybe me and Ave that I'm hilarious.
Oh, I think you're very funny. Very funny. Yes.
Have you ever tried to graph a perfect stick figure using
This
Desmos?
is tree. Wait, you please do. You probably could.
We can do that.
Yeah, you'd have to do a line, like couple line segments.
I'll give myself 1
Out of
minute.
a
That's
circle.
all. Okay, so you gotta do we gotta put a circle on there, right?
Yeah.
So x squared
could.
plus y minus like 2 squared equals 1. There's a circle. We need the hard part's gonna be how do I get the segment here?
Piecewise.
Line.
Well, it's like
Yeah, but it's maybe I'll just make them
cheating.
we gotta I'm gonna make them kind of sideways.
like, couldn't you do like
You can.
y equals 6 and then
Wait, it's not sideways, will you not be able to see it?
Well, I'm just not sure if you can do a piecewise function.
well, couldn't you just do a vertical line and then put it in between
Hear that first.
two
That's
y
supposed to be
values?
his neck or his body.
That's his body.
Oh,
Yikes.
Well, yeah.
can you make him have
What
eyes
are
and
you
a mouth?
doing? So I'm gonna do it.
There's a lot to ask here.
A
She
smart.
has sad face.
A sad face.
I'm gonna
Sad
do
face
my
for you,
body,
Lily?
but yours-
Are you going with it?
Yeah.
One of those.
Okay, here you go, Lillian. Sad face for you. This might be a little trial and error here.
Okay. Well then,
It's a mustache.
Oh, sorry.
you should move that down to the arms, J Hall. That'd be good.
Huh?
That'd be good for the arms if you did it down more. Just saying.
They got only sad
There you
noodle
go.
arms, though.
That's okay. No, it just means that he's like bulking up.
Great color.
Can
Yes.
you make his arms curve?
That's what I was saying.
Jeez, I don't know.
Why you got funny noodle?
You wanted him to be sad, didn't you?
Oh,
Then his arms need to curve down.
he's sad because he has funny noodle
Yeah.
arms.
Yes,
Yeah.
Trenton.
He's sad because he doesn't have a schnoz. He needs a schnoz.
You guys are asking a lot here. Oh my god.
What is that?
I just looked up. Oh my god.
He's making a little.
Give him
That's his leg. God,
Tripod.
stop. This is funny. Nice.
And then I think I'm done.
This is working really good. This belongs in some sort of pool.
This is the most beautiful thing ever. Beautiful. Oh
There you go.
God.
He's done.
Artwork. Woo! True artwork. Beautiful. I have to take a picture. I'm gonna. I'm also trying.
I forgot I was recording class. I guess if Griffin's watching this, he's like, what are they doing? Sorry, Griffin. Sorry, Griffin. Okay, let's get back to work here. Okay. There you go. There you go. Desmos, you can draw a
What's
picture.
his name?
Desmond.
I don't like that.
Desmond.
Desmond, I like that name.
So,
Nice save.
okay, so number 3 involves 2 thingies that are kind of challenging. The first thingy being that you got to use the product rule here. This is a product of 2 functions. Okay. Just forgive me if I say functions. It's not technically y is not a function, but close enough. I have 2 things here, so I got to use product rule. So that's that idea of if you have a times b, the derivative is a prime b plus b prime a. Now back to the thing we were talking about earlier. When I write this statement out, that's assuming we have some third symbol that we're taking the derivative with respect to. So to write this very complete, it would be, the derivative with respect to, say, x of a times b is a prime b plus b prime a, where a prime represents dA over dx, and b prime represents dB over dx. Okay. So, derivative of him is 3y squared y prime. So it's derivative of him times him. So look at that first term. That thing's a mess.
Yes,
It's
yes,
got
it is.
3y squared y prime, that's the derivative of the first dude, times x, which is just the second dude, not derivative. And then you go plus, what's the derivative of him? 1 times that dude. Okay, so before I move on, any questions on that derivative there? Yeah?
Why did you put that X behind the Y prime?
Because we're basically using you're using the product rule here. So you got to think of this y cubed as being like the A.
And then the X is like.
The X is like the B. So
Okay.
basically that B just ends up like right there in that first term, which is why we see the X there. Okay, any other questions? Okay, so then derivative of x squared is 2x. What's the derivative of 5y? 5y prime. Are we okay with that?
Yep.
So the derivative of y is y prime. The derivative of 5 times y is 5 times y prime. Okay? Now, Do you guys see what part of this, what makes this one a little bit trickier than the last one? There's two y primes, exactly. So it's not too bad though. We just gotta get them on the same side, factor about, and we'll be fine. So first step is rearrange it. So get this guy to the left side, get this guy to the right side. Hopefully that makes sense, right? Pretty straightforward step. And then we're going to factor out y prime. So this guy, if I factor the y prime out of him, what's left over is 3y squared x. And what's left over from him is just a 5. We're almost done. So it turns out the derivative is, so then we just divide both sides by this quantity here, that expression. And there you go. That's not the most prettiest thing. Not the mostest prettiest. Interesting. Watch this. Oh, God. Like tears in rain.
Bye, Desmond.
Oh my god.
Okay.
So what I want to show you here, guys, I think it's very interesting. So this is a pretty weird looking curve, right? Oh. Okay. So try to stick with me here, though. I think this is very interesting. So weird looking curve, right? Look at our final formula. Do you guys see why our final formula tells us that the only places that this, I'm going to write it down actually, the only places where this could have a horizontal tangent line, if there was a horizontal tangent line, then this thing would have to be 0, right?
Yeah.
Which would mean that 2x minus y cubed would have to equal 0. So what if I graph that curve? 2x minus y cubed equals 0. Notice that it's going to pass through the two spots where this curve actually does have a horizontal tangent line. Moreover, that's a really weird one. In order to have a vertical tangent line, the bottom of the fraction would have to equal 0. And if I draw that curve, 3y squared x plus 5 equals 0. 0. It's getting a little cluttered, but do you see how it hits that one point where there's a vertical tangent line? So it's I think it's pretty interesting to look at how, so the points that live on this curve and this curve at the same time would be your vertical tangent line spots, and then the points that live on this curve and this curve simultaneously would be your horizontal tangent line spots.
Cool.
So, all right, let's do one more. What do you guys think? Does this stuff seem super confusing, or does this make sense?
It's getting. I like it. I'll absorb it.
Okay.
Give me 1 or 2 more days. Then I'll. See the other way. The other way.
Look at number 4. Ask
Oh,
yourself, what is the way to proceed here? This is the way to proceed.
We have to use the quotient rule.
Quotient rule is certainly a good option. Yeah, I like that way. There's one more way You could rearrange it so that it read, if you multiply both sides by x plus 1, you could have y squared times x plus y squared equals x, and then proceed using the product rule. Might be interesting to look at how those two methods kind of like.
So I'll do that.
You're going to do that? Okay. I'll show both on the board here just so we can see. With implicit differentiation, you often have some flexibility of how you maybe you can manipulate it algebraically before you proceed. But so anyway, let's do the quotient rule way first. So let's refresh our memories. The quotient rule tells us that if you've got like a over b, your derivative is going to be a prime b minus b prime a all over b squared. That hopefully rings a bell. So okay, let's do that on this guy. Left side's a bit easy, right? Just use the chain rule. 2y times y prime. The right side we're going to use the quotient rule on. So a prime is just 1. So 1 times x plus 1 minus 1 times x all over. Are we all cool with getting from there to there with the quotient rule? Yeah?
Yeah.
Yeah. What's the top? Actually. It's just 1, yeah. 1. So, turns out the solution didn't involve that much algebra, really. The top is just 1, because you have 1x minus 1x, and then you just have that 1 left over. So if I divide both sides by 2y, there you go. So for a yes, it did.
Why don't you cancel out that, just take away that exponent on top? Which leaves you negative.
So that would be, yeah, that's not going to be okay, because if I divided that by x plus 1 and canceled it out, then I'd have to also divide that one. You certainly could do something like split this into a pair of fractions, like that divided by that would be 1 over x plus 1, and then that over that would be x over x plus 1 squared. That's an option, but I think it's much simpler to simplify the top before you. That makes sense? Oh, okay. For a million bajillions, can anyone, by looking at this and this at the same time, tell us where this thing would have a horizontal tangent line?
Nowhere.
0. Good job. Nowhere. Because a horizontal tangent line would mean the derivative was 0. Can this thing ever equal 0?
No.
No. Good. So that's great. A little bit trickier. Where would it have a vertical tangent line?
wait,
Where
that's
the
what was
bottom equals 0.
If the bottom was 0, right? So if the bottom was 0, so there's 2 ways for that to happen, right? If x is negative 1,
Yeah.
well, wait a
okay,
second.
okay.
Is x allowed to be negative 1?
Mm,
I don't think so.
No.
If x is negative 1, then I'd have an undefined fraction over here. So the other option would be, what if y was 0? Can y be 0?
Yeah.
Yeah, because if y is 0, x just has to be 0, and then both equations satisfy. So from looking at this, it seems like if we graph it, we'll have no horizontal tangent lines, and we'll have a vertical tangent line at the origin. So let's see if that actually works out. Y squared equals x over x plus 1. And we can see, indeed, there's going to be a vertical tangent line at the origin. And it is interesting, though, do you see there's no horizontal tangent lines, but there's horizontal asymptotes. And there's certainly a connection there, right? So you might say, oh, as x approaches -1, you're sort of approaching a vertical tangent line. And as x approaches infinity, you're sort of approaching a horizontal. Okay.
Were you
I
gonna
always
do
forget
it
what
the
time
other way
class
too?
ends.
58.
Okay, let's do one more.
Wait, were you gonna do it the other way as well?
Oh, did you finish it?
Well, I don't think it's right, so.
You should end up with this, hopefully. Oh yeah, you look the other way. The other way would be that I was suggesting earlier. Thanks for reminding me. Would be if I just manipulate this equation before doing any of this. If we just manipulate that, multiply both sides by x plus 1, you end up with that, which I think would be nice to just write that as y squared x plus y squared equals x. And so now you go 2y y prime x plus y squared plus 2y y prime equals 1. Did I do that right? Because that's
A lot of Y's.
product rule on that will give me this. 2y y prime times x. There's my a prime b plus b prime is just a 1, a. And then the derivative of this guy is 2y y prime. And the derivative of x is 1. So I think that's correct. It seems right. And then factor out a y prime from this pair, this dude, and this dude. So y prime times the quantity 2yx plus 2y. And then the right side is going to be 1 minus y squared. Does that seem right?
Yep.
And then divide. Let's see.
And then you get 1 minus y over 2 x plus 2, or 2 times x plus 1. And that's where I was.
Like that.
Yeah. Yeah, yeah, yeah.
Yeah, where do we end up with the extra term?
Yeah, that's my question.
It's probably because, so maybe I was jumping the gun there, because I think maybe a problem with multiplying both sides by x plus 1 is now if you look at this, it seems like you multiply both sides by 0 if x was -1.
Yeah, and also, yeah.
I don't know, I'd have to maybe think about that some more, but yeah. So maybe that's a good argument for try not to manipulate it too much. Because this, if you look at the graph here, does the graph agree with, the graph agrees with the first one the best, right?
Mhm.
Because this seems to suggest that that y can be 1, if y was 1. Well, part of me is thinking that maybe these are somehow equivalent in like a weird way.
Yeah, that's what I was.
I think there's some substitution you could do where you could say that maybe like a, because notice this is missing a little squared down here. Anyway, I don't want to take up too much more time with this one problem, but
Multiplying both sides, could you put the x plus 1 up on top and just put it to -1? Would that work? Since, or is that basically doing the same exact thing?
Yeah, like
Do what?
treat it as x plus 1 to the negative first power, and then do a
I'm
product.
pretty sure that's.
that would be totally equivalent to this, yeah.
I was gonna say, would that do the same thing?
Oh, you know what? I think here's a substitution. If you replace this y, let's see if this works out. We're almost out of time anyway, so we can just wrap it up.
This is well experimented.
So that y squared is equivalent to an x over x plus 1. So if you write this as, this would be a mess. If you write it as 1 minus x over x plus 1, So replace the y squared with x over x plus 1. And then the bottom just looks the same. And then to get rid of this fraction inside the fraction, Johnson and Johnson's no more tears formula, multiplied by x plus 1 over itself, gets you x plus 1 minus x, which is 1. And then the bottom. So it turns out
Oh,
it was
God.
fine.
It was fun.
It's just that to actually get it into this more nicer looking form, you had to.
Yeah.
Oh, this is a bad form. It looks
No,
fine.
it looks fine. So I was right. At first I was like, what the heck is going on here?
That happens from time to time in calculus where you're like I know I did. The only thing I was worried about is like we multiply both sides by x plus 1, which should be fine as long as x isn't negative 1.
Yeah. Which, yeah.
And so yeah, it just turned out that we needed this weird substitution.
Weirdo.
Weird.
Yeah, Jesse, I don't think I've ever said in my life during math. Oh, I know I did that right. Ever.